Hi everyone, and welcome to Physics 120 remotely. So this is going to be new and different for all of us, but we're going to try to have the best experience that we can. So in this first class video, I'm going to spend some time talking about the theory behind the pendulum experiment you're going to be doing remotely or watching me do over the next 2 weeks. Now, the physical system we're going to be investigating is pretty simple. It's this. So this is a pendulum. I've tied a metal ball bearing here to a piece of string. And if I pull this out and let it go, you can see that it swings. Now, if you watch the swinging carefully, you might notice that the period, that is the time for one complete swing, maybe it looks to you like it's pretty constant. The goal of your pendulum experiment will be to analyze the swing, to analyze the period of the swing, and figure out what it does and doesn't depend on and how it varies. So in this video, our goal is to do the following. Okay, so we're going to argue that the period t of a pendulum is going to be given by 2 pi times the square root of L over G when the angles are small. And I'll say more about what that means when we get there. Now let me just be clear about our symbols here. T is our period. G is our free fall acceleration. And L is the length of our string. Let me define that precisely. So if I have a pendulum where I've got the string hanging from some support point, and then I actually have some swinging object, which we, for some reason, always call a bob. The length L is defined as the distance between the support point and the center of mass of our bob. So let me just label that to bob, center of mass. Now, there are 2 ways we could try to establish whether why this equation might be valid. So in some ways, the more fun one is the one that we're going to do together. That is, doing an experiment. The other way is to apply physical principles or work this out in theory. So we're going to focus on this approach in this video. I'm going to just tell you what steps I'm going to take in broad strokes before we dive into the weeds. So here, what we're going to do is we will use Newton's laws to derive a differential equation of motion for a pendulum. To derive pendulum equation of motion. So we'll derive this equation of motion in general for all angles. Then we'll use what's called the small angle approximation to simplify that equation of motion to something that turns out to have a nice solution. Simplify with small angle approximation. What we'll then do is show that the simplified equation admits a solution that's periodic or sinusoidal, admits a solution with the period t I claimed up there. So let's proceed with our analysis. Now, the first big insight you really need to take about pendulum is that when I have this bob swinging, it's not swinging in a complete circle, but it is swinging in a circular arc of radius L. So this is helpful because we can take everything we learned in Physics 117 about circular motion and apply it to this case. So let's draw a picture here. So here's my string and my bob. I'll draw a dashed line to denote the vertical here. Oh, my marker died. I'll grab another marker. So, a few things to note, just as we start to set up the analysis of this. Let's first start by thinking physically about the motion. So if you watch the swinging pendulum, you might notice that the bob is going to sort of have a turning point up here, where it momentarily stops and changes direction. It's speeding up as it swings down through the bottom here. At the bottom, the bob is going at its fastest speed. As it swings up, it's slowing down, right? Until it reaches its turning point up here, whereupon everything reverses. So it starts swinging back this way, speeding up, right? Going through a max speed down here, slowing down, and then reaching back to its turning point. So let's, in order to sort of analyze what's happening here, we're going to want to think about the forces that are acting on the pendulum bob, but it'll be helpful to establish some conventions. So let me establish that, by definition, theta equals 0 is vertically straight down. I'll also assume that right now, as I've drawn it, the pendulum bob is at some positive angle theta over here. So I'll call the positive angular direction to be counterclockwise from the vertical. So And what this also means is that, remember when we talked about circular motion, right? We talked about radial and tangential, right? So I'm going to take the positive tangential direction to be also counterclockwise. Alright, so now let's think about what forces might be acting on the pendulum bob. Before I draw the free body diagram for this, I'd like you to take a minute to think about what forces might be acting on my pendulum bob. Now, you've had the chance to think about the forces, so let's see what you came up with. So I would argue that, right, as maybe you've heard somebody say before, that you want to think about both contact forces and non-contact forces acting on our pendulum bob. So, just like we do with free body diagrams, I'm going to draw a dot to represent the object under consideration, here the bob. So thinking about contact forces, right, we know that the only thing touching our bob is the string, right, and so that string is going to exert a tension force. And I'll just label that T. That looks something like this. Now, the only long-range force we care about in this context is gravity. So I'll also draw the gravitational force F sub g exerted by the Earth. Now, because this is motion in a circular arc, we're going to want to draw a useful coordinate system here. And the useful coordinate system we'll take is the radial and tangential system. So at this instant, the tangential direction, so I'll label that T for tangential. And then I know different people have different conventions for this. If you used Knight in 117, Knight likes to define the radial direction as being positive, pointing inward. I'm not the world's biggest fan of that, but that's what we did in 117, so I'll go with that. So now we can proceed to apply Newton's second law component-wise. So Newton's second law, you know, says that the acceleration, or the mass of our bob, this bob has a mass of m. I forgot to label that. The mass times the vector acceleration of the bob is equal to the net force on the bob. Now, because Newton's second law is a vector equation, we can break it down into components. So we have, we have both a radial and a tangential component here. So and so we have m times the radial component of the acceleration equals f net radial. So this is again a vector component. And similarly, Newton's second law holds for the tangential component, a tangential equals f net tangential. Now it turns out that the radial component isn't super interesting for us. You do know what the radial component of the acceleration is. It points radially inward, and it has a magnitude of v squared over, in this case, L, because L is the radius of the circle. But that's not really going to be helpful for deriving the pendulum equation of motion. So not. Instead, what we're going to do is to focus on the tangential component of Newton's second law. Now, F net tangential means we have to sum up all the forces. So we've got to think about the tangential component of gravity, so I'll label that T, of the tension, sorry, T sub T, as well as the tangential component of the gravitational force. Notice, however, that the tension by the string only points in the radial direction. So this component actually goes to 0, and all we have to think about is the tangential component of the gravitational force. So what I'm going to do now is I'm going to redraw the gravitational force vector and do a little bit of geometry to help us find the tangential component. Alright, so I've blown up the gravitational force down here. This dashed line is representing the string, or the radial direction. And when we think about breaking this gravitational force into components, I can draw two component vectors, right? So I can draw this vector as the sum of a vector in the radial direction. So here is component vector fg sub r, and then plus a vector in the tangential direction. So here's my fg sub tangential component vector, and let me label in the fact that we have a right angle here. Now, if we think about the angle theta here, right, it's the angle that the string makes from the vertical, right? Now, gravity, we know, acts in the vertical direction, but this, the radial direction is the same as the direction that the string makes. So, in fact, we actually have the angle theta right here. So, now it becomes a matter of geometry, right? We're trying to find the component Fg sub t, the tangential component of the gravitational force. And that, right, a vector component, it's a magnitude and a direction, right? Or it's a magnitude and a sign, rather. Right, so I want to know the length of this piece down here. And I need to think about the sign. Does it point in the positive tangential direction or the negative tangential direction? Maybe let's do the direction piece first. Right, notice we've defined the tangential direction here such that counterclockwise, or that way, is positive. Here, Fg tangential points in the opposite direction. So we already know that the tangential component of the gravitational force has to be negative, since it points not in the positive tangential direction. Then we just need the length of this piece, the magnitude of component vector Fg sub t, And we can get that with a little geometry, right? So notice that we've got a right triangle, right? So the length of this side is opposite my angle theta. This, my gravitational force vector, is the hypotenuse here. So it turns out that sine theta, you'll remember that's opposite over hypotenuse, so that's going to be the magnitude of f g t over the magnitude of the gravitational force f sub g. So vector component is sine and the magnitude of component vector. So we got this from the geometry. Plugging in over here, we have, so the magnitude of this component vector is, so that's just the magnitude of fg times sine of theta. But we know that the magnitude of the gravitational force is m times little g. So this is none other than mg sine theta. So at this point, we can go and put this in to Newton's second law. So returning to that tangential component, we have ma tangential equals f net tangential, which we said was just the gravitational force because the tension is purely radial. So we have minus mg sine theta over here. Notice that I have a common factor of m on both sides. So if I go and I cancel that out, divide both sides by m, I get a tangential equals minus g sine theta. Alright, so where can we go from here? We've got the acceleration. We've shown that it depends on my angle theta. But mathematically, it turns out this isn't super easy to deal with because we've got sort of two different variables here. We've got a linear acceleration, and we have something that depends on an angle here. What we will want to do is rewrite this tangential linear acceleration in terms of an angular variable. So again, recall from Physics 117 that I can relate linear acceleration to angular acceleration for something that's undergoing circular motion. So in particular, my tangential linear acceleration is going to go like my angular acceleration, alpha, times the radius of my circle. And here's the part where we need to remember that the pendulum is swinging in a circular arc of radius L. So we have AT equals alpha times my L. Well, my alpha, my angular acceleration, is none other than the second derivative of my angular position, my angle theta, just like linear acceleration is the second derivative of position. So if I'll write the L in front, we can actually write this write this A tangential as L times d squared theta dt. Plugging that in, right? So bringing these two pieces together, we get the following. We got d squared, we have L d squared theta dt equals minus g sine theta. Or to write this in sort of the traditional form, noting that now theta is a function of t. We're trying to solve for the angle theta as a function of time, ultimately. That's I'll write it out the full dependence. So so we get d squared theta of t dt equals minus g over of L times sine theta of t. This now is the pendulum equation of motion. So and it's valid at all angles. So valid. Right. We didn't make any approximations in deriving this. We just applied Newton's second law. Now, this is what we call a differential equation. So this isn't a diff-EQ class, so I'm not going to dwell on techniques for solving this. But it does turn out that this particular differential equation isn't straightforward to solve analytically. So what I'll do is I'll erase the board, but what we'll next do is apply what's called the small angle approximation to simplify this. Alright, so here's our pendulum differential equation. Now it turns out that the problem with this equation is the sine function here on the right-hand side. So this is where the small angle approximation comes in. Now I won't go through test cases in detail here since we're going to ask you to do that in homework, but it turns out that when you measure your angles theta in radians, it doesn't work in degrees, only in radians, then sine theta is approximately equal to theta when theta is much smaller than 1. So what does much smaller than 1 mean? Well, it typically does depend on sort of how good you want to get. But rule of thumb, theta less than 0.1 radians, you're doing pretty well. And you'll, in the homework, explore sort of the validity of this in more detail numerically. Now, if you've studied Taylor series in Calc 2, I think, you might recognize that this is just the first term in the Taylor series for sine. That's exactly what it is. But then the fun bit is that if we apply the small angle approximation here and plug it into our diff-EQ, this gives, I'll drop the time dependence now explicitly, so I'll write this d squared theta dt squared. This gives me minus g over L theta. This is now the simplified equation of motion, but that's only valid for small angles. So simplified so what we'll do next is we'll solve this simplified equation, or show that it admits a solution with the properties we want, and then we'll prove that the period, if this equation is valid, is in fact 2 pi root L over G. As we do that, I'm just going to introduce one piece of notational simplification for convenience. This is kind of arbitrary. I'm doing this because I know how the game is played here, so don't be alarmed if it seems like you wouldn't have come up with this sort of trick on your own, because it's not obvious. I'm going to help myself out here by, I'm going to define a constant, omega. I'm going to define that, Greek lowercase omega, as the square root of G over L. What this means is that my differential equation then turns into d squared theta dt squared equals minus omega squared theta. Okay, so we have our differential equation here, and now what I'm going to claim, our simplified differential equation, what I'm going to do is I claim that the following is a solution. So I claim that theta of t equals some constant theta naught times cosine omega t is a solution to this differential equation. Now, this seems like I'm just pulling something out of thin air. It is a pretty common thing in differential equations to sort of postulate or guess that there might be a certain solution. We do know that pendulums oscillate, but then what we just need to do is to prove that this claimed solution really does satisfy this differential equation. And we can do that in the following way. We'll take this proposed solution for theta of t, we'll substitute it into the left-hand side, calculate the second derivative, and if all goes well, we'll see if it actually equals minus omega squared times theta. So let's go ahead and do that. So we have d theta dt. So I'm assuming theta naught and omega are constants here. So if I take a derivative of this, I can pull out my constant. Now the derivative of cosine is minus sine. So I get a factor of -1, and then I have sine omega t. But I have to remember that I need to use my chain rule here. I'm taking the derivative with respect to t, not omega t. So I need to differentiate this bit with respect to t. Omega t is just a constant multiplying t, so taking the derivative with the chain rule gives me another factor of omega. Let me simplify this and just collect everything together. So this gives me minus omega times theta naught sine omega t. Now, the second derivative of this, I just have to differentiate it again. Now, this time, again, I have a bunch of constants, so minus omega theta naught is all constants. Now, the derivative of sine is cosine, as you might have guessed, or remembered, hopefully, from calc. Once again, I have to use the chain rule on the argument of the cosine function here. So d dt omega t gives me one more factor of omega. Collecting everything together gives me minus omega squared theta naught cosine omega t. Lo and behold, right? Our second derivative of our claimed theta of t is none other than minus omega squared times the solution theta naught cosine omega t, right? So we have equals minus omega squared theta of t. So we have indeed shown that this is a solution of this simplified differential equation. I'll put a check there to indicate the claim has been verified. Now, this is not the only solution, it's not the most general solution to this differential equation. That's a detail I'll leave to, I guess, either Physics 217 or a differential equations class. If you think I have brushed a little bit under the rug, I have, but this will do for our purposes. So our last step here is to show that this claimed solution gives me something with a period that is 2 pi root L over G. Alright, let's take a look at this solution. Probably the best thing to do with it is to graph it. So let me plot this theta of t here. And I'll, just to make things easier for me, so I'll plot the combined variable omega t rather than just t, because it might be easier to think about that. And then let me just label theta naught over here and minus theta naught. Well, what does cosine look like, right? So at 0, cosine equals 1. So at omega t equals 0, theta of t should just equal theta naught. So we have that point starting over there. What else do we know about cosine, right? So let me just draw in. So know your unit circle. It's really helpful. So here's pi over 2. Here's pi. Here's 3 pi over 2 and 2 pi. Right, so you might remember that cosine of pi over 2 is 0, as is the cosine of 3 pi over 2 radians. And that at theta equals pi, cosine goes to minus 1. So theta goes to minus theta naught. So, and that back at 2 pi, right, we are back at cosine of 2 pi is equal once again to 1. So we can already kind of piece together the shape of this. So if I do that, I'm going to get something that looks like this. And my drawing of my hands are a little wobbly, but I think you can see that this is periodic, right? In that one full period happens, so it's a time at t when omega t equals 2 pi radians. So this now lets us determine what the period is. So namely, so if omega times my time t, so when we're at one full period, so I'll just label that capital T. So that's 2 pi. So one period here. Well, now I just need to plug in my omega over there. So if I have my omega, which I defined as the square root of g over L, multiplying my period, capital T, equaling 2 pi. Now, I can solve for my period. If I just divide both sides by root g over L, I will get T equals 2 pi. So I just need to flip this upside down, times the square root of L over G. And that's what I claimed we would show at the beginning. Now remember that this is only valid for small angles, because this solution to the simplified differential equation is only valid when theta is small. This is a small angle, a small angle solution. So we can see that the period appears to depend on the length of the string, as well as the gravitational acceleration. Notice that it doesn't appear to depend on the mass of the bob. Now that's a concrete prediction that we're going to be able to test experimentally. Okay, so I'm going to wrap this video up now, but when we come back, what we'll do is we'll talk about the measurement circuit for the pendulum experiment and how you'll need to modify the timers you've already built in order to measure the period of a pendulum.